So now that you've made that combined thing, make sure that it's a factor by using as.factor. While you guys work, I'm going to run my stuff down to the point where we kind of are. Oh, that was easy. I had it all in one code chunk. So what you should get at the end of this is you should have a data frame that's 182 observations with 5 variables. One of those variables is a combination of the population and the season, and the structure of it should look like this. And it doesn't matter what you call that combined thing. I called mine PS just to save myself keystrokes. So when you have your data set looking like this, and you have this as a factor, put up your blue tab. You have an orange tab. Yeah, what you got?
This is
That is weird. So that's your data frame, right? Looks exactly what you wrote, right? Wait. This is a tidyverse thing, so you need to add, you haven't added any packages yet. So you need Pacman to come to your rescue. Here it is. Obviously, if you haven't loaded any packages yet, then you're not going to be able to rely on packages like tidyverse in order to do the filtering. So don't forget, at the top of every script, you should have a list of packages that you suspect you're going to need. In this case, we're going to need ggplot, we're going to need rmisc, we're going to need car, we're going to need the tidyverse, we're going to need agricole eventually. As soon as you get tidyverse in there, that will work, Clara. Don't forget the packages. Karis isn't going to be here. Do you want to just move your seat so you can see the screen easier? Yeah, Cole, what's up?
Yes. I'm trying to filter this data.
Okay.
That's right.
All you need is type. You don't need that $, because you've already told it what the data frame is.
I didn't. Just gave me.
I know. Okay. All right. So. Okay. What packages do you have loaded?
These are the ones I loaded.
All right. Add tidyverse. And it should be the same as tidyr. Just in case. Yeah. Go ahead and run that. Okay. Just go down to the filter. So do now. You now have 0 observations. Yeah, so something happened somewhere. $1,255. Okay. So now you're going to change this to a factor. That is now a factor, and it has 4 levels. Oh.
Oh.
182. Yeah. We talked yesterday. Typing is going to be your downfall. So always. So your thought should be the same as my thought. Whenever I have an error, I don't usually think that R is doing something wrong. I usually think I've mistyped something. And so the first thing that I try and check is, have I left out a comma? Have I misspelled something? Have I dropped a character when I was typing out a variable name or something like that? That's always my first step, is check my own typing errors. For you, some of you are probably better typists than I am, but that's always my first go-to. Did it work?
Yeah.
Okay, yeah.
On 7,
Uh-huh.
make a new variable that combines them.
Okay, so what are you trying to combine? You're trying to combine population and season. Mm-hmm. So what you can do is just make a new variable. In mine, I made my variable short and sweet so that I don't have to type a lot. PS for population and season. Use the assignment operator. And what you want to do is you want to paste what is in the data frame population column, and you want to paste it to the data that is in the season column. And close that off, and what it should give you is a new variable that should just be the population and the season. So we had population and season. I'm just pasting population in there and then pasting season in there. So now head your data file again. Head. Sorry. You need to have your data frame in there. So it's going to put that new variable. So it should be $$PS. Oh, because I didn't write it on the board. You always have to tell it to put that variable into a data frame. Yeah.
Get this started, right?
Let's see. So you've read in your thing 1,255 variables. You've changed population to factor. You've changed season to a factor. So let's look at the structure again down here after you've done all of that. No, just rerun that same line because you've changed that. So now these things are as factors. You might want to have type as a factor also. Same way you did it up here. So, whoa, where did you do it? Oh, same way you did it here. So just do $type as factor. Yeah, same thing. So these are all categorical variables that you're going to be using in your ANOVA. Nope, because you want to change type. You want to change type, the body temperature type. Nope, $type. That's your data frame, and you're changing the column type in it. Yeah, and then that's going to be as factors, correct? And then $type. So it's the same syntax as you used for these. Now run structure again, and it should show you type as a factor. Type is now a factor. Okay, so now go down. So you need to filter. So filter that. Yeah, rerun it. Because you still have 1,255. Why did that not? Oh, whoa, what is data frame? Data frame is just my word for whatever your name of your data frame is. So for you, it would be DAT. Yep. Mm-hmm. It's looking for something that doesn't exist. Now run it. Okay. That's weird.
Do I need another one of these marks? I think I might have erased it.
Oh yeah, you do need another one of those marks. You did erase it. All right, now try it. There, yeah, good job. Yeah, nice. Now go back and run structure and make sure that it is the, should now only be 182 observations. Okay, good.
Levels.
Levels is when you want to check the levels of a particular variable. So you would put parentheses. Nope, just levels, and then parentheses and whatever variable you want to check. So dot type, for example, or not $sign type. Yeah, and then that'll tell you whatever. That'll tell you whatever levels are in there. So you've got 4 levels, but you don't really have 4 levels. It's recalling 4 levels from previously, but you only have 182 observations because you've gotten rid of all of the levels except for body temperature. So if you went and viewed your file, so do view for your data frame, view dot, you have to do, yep, there you go, you have to tell it what you want to view. As you scroll down, it should only go to 182, and all of your temperatures should be body temperatures, all the way down. All right, coming around.
I think I got it. I just have a formatting question.
Mm-hmm.
I don't know what I did to make it change where it's showing the things up there now.
Go up here to because you started with a new script, tell it to put the chunk output in the console rather than inline and remove all of that output. Now that cleans up this space, and anything you do here is going to appear down there. Yep. That's something I usually forget to do until I start getting irritated at it cluttering up my space.
I'm trying to filter. I don't know if that's the correct code up for that.
Nope, it is not. Because remember, what you're wanting to do is you're wanting to overwrite your current data frame with a new data frame that just has the body temperature data. So you need to start with, you want it to overwrite the data frame DAT. So use the assignment operator to overwrite it. And then what you're going to do is you're going to filter the original data frame, and you're going to filter it by type, 2 equal signs. So it's basically saying, I want you to filter the data, the DAT data frame, but I want you to filter it by only including those things that have this in the type column, and then save it as DAT. So try that. That should work, if I remember the syntax correctly. Now you're done. All right. What is type underscore update? You're making a new, what is that? What are you trying to accomplish here?
That was changing factor.
Oh, so you're not creating a new variable there. This should just be that. If your data frame is X, then this should be X $ type, because you're basically just saying, I want you to save X $ type, but I want you to save it as a factor.
Oh, okay. So how do I get rid of like the old data? This is like old data I had from.
Just go back. So one of the things you can do is you can just clear out everything. Now this means you're going to have to start over.
Okay.
And yeah, just start at the top. So that looks like, let's get structure of X. Let's clear out this also. So you can use these sweep things just to clear out old junk. So that, let's do this also. Let's make it put chunk output in the console. That cleans up your workspace here. So now structure will appear down here. 1,255 observations. You got season, population, type, and temp C. So now this is messed up because this needs to be, I want to make X $ type into a factor. So it's just basically saying, take this thing, convert it to a factor, and just put it back where it was before. Then when you run that, if you run structure again, it should now have that as a factor. as opposed to a
okay.
character
I
before.
didn't reach
Okay?
Deviation.
Yeah, whenever I'm doing this initial cleaning up and organizing of data, you will see in my scripts, I do something and then I run structure, and then I do something and then I run structure, and then I do something and I run structure, because I want to see that R has done the thing that I asked it to do. Don't trust R. It's a machine. It's going to get artificial intelligence. It's going to come to rule the world and stamp out the human race. You have to keep your eye on it every moment. Yeah.
So that's not how I combine them.
Okay. So you did paste that that season. Okay, so let me see. Just head your data file. I don't need to see the whole thing. Oh, because it looks like it did it right down there. Yep. Okay, so there's your new variable. It's a combination of population and season, but you see that it's a character and you want it to be a factor ultimately. So change it to a factor. How do we do that? Mm-hmm. Notice in the drop-down menu, it gives you your choices. The bottom one was PS. Yeah. Then run structure again, and it should have changed it to a factor. Boom, chicka boom.
Yes. Okay.
182. All right, cool. So everybody should have a data frame, regardless of what you're calling your data frame. You should have a data frame that when you take the head of it, it looks like this. Is that correct? All right, tabs down. Okay, we did all that. We did all that just to get ready to do an analysis. Okay, so I got this question from, I forget who was it that sent it to me yesterday, but he's like, what do you mean by clean up the data? This is what I mean by clean up the data. Clean up the data. Verify that the data frame that you're working with is the data frame that you want. Make sure that it only has the data in it that you need, and that those data are complete, included, and that you've done some housekeeping things such that you've combined these two variables into a single variable, because all you guys know how to do at this point is you only know how to run a single factor analysis of variance. You don't know how to do a two-way analysis of variance because we haven't taught you that yet. So we had to get these two factors combined into a single factor, and that's what we did when we used the paste command. So this is just getting your data frame to the point that you can actually do something with it. Now that we have the data frame in such a way that we can do something with it, what do we want to do? It's the first things we should do in an analysis. We should check for normality and we should check for homogeneity of variances. So the first thing we have to do is we have to specify a model. Once again, the model is an analysis of variance. So I'm just calling my model Model 1 because I might have multiple models, so I'll just number them throughout the script. Model 1, use the assignment operator to tell R that whenever I type in Model 1, I want you to run an ANOVA, where it looks at variation in temp C as it varies by whatever my combined treatment level is. For me, that's PS, and use the data frame DAT. And when you do that, and then you get the summary of the model, it should give you an analysis of variance table. So run those two lines. When you've done that and it worked, put up your blue tab, and if you do it and it doesn't work, put up your orange tab. My watch says I've already walked 2,000 steps, and I think I've walked most of them in this class, in this classroom so far. Oh, what are you having troubles with? Okay. Run structure. Again, let me see how R is viewing everything. Oh, you made temp see a factor. That's numeric, actually. Because that mess up that we made earlier, yeah, because I wrote it on the board wrong. So instead of typing as.factor, type as.numeric, and that will convert it back to numeric data. Yeah, that's the problem there.
I'm saying MC is not found. I have it. It says it's right here. I ran it.
Okay. Oh, tilde. This is a
Oh.
tilde between temp C and PS. Wait, well, no, let me see.
No.
Yeah, that's a tilde, not a. I think you got a dash in there. So.
This should work now. Okay.
Yeah, there it goes. Yep. What the tilde means in these code lines, what you're basically saying to R is, I want you to do an analysis of variance, and I want you to look at variation in temp C as it is affected by the combination of population and season. So tilde, you can just put in the words as it is affected by. So this is your dependent variable, and this is your independent variable. Your independent variable presumably affects your dependent variable. So this is saying, how is temperature affected by the combination of population and season? Where am I going to go and get the data for that? I'm going to get that from my data frame, whatever my data frame is. And so that's kind of what the syntax means in plain English. Your tab is still up, or did you get it? Okay, all right, got it. Everybody get it? Yeah.
Would this be a good way to explain what asking R to look at Team CS and it's affected by?
Yeah, yep, that's exactly what you're doing. Yeah. And good that you're annotating code. Claire is annotating code as she goes, so she's writing little comment statements in her code blocks. So she, right before she did Model 1, she has a line and a half of explanation that basically is explaining what the next line of code is doing. And that's good to do if you have time to do it while you're doing it on the fly. If you don't, go back after class and annotate your code so you don't forget what we did. All right, so tabs down. So the first thing we have to do is we have to test assumptions. The first thing we have to do is run a normality test. So the first thing that we have to do is we have to generate the residuals. I'm not going to save these as a column in the original data frame. I'm just going to save them as an object. So res1 are the residuals from the model, and you can get a big long list of those. Blue tabs up when you got 182 residual values. Did we go through all this in my office the other? Yeah, that's why you're ahead. And I called mine res1 simply because it's the residuals from model 1. You will see that I get in this habit of being fairly rigid about how I name things. I don't ever have to remember where residuals from model 1 are because they're in res1 because that's the first model that I ran. That's model 1. Blue tabs up when you have it. Orange tabs if you hit a snag. Oh, your hand went up, and I thought you were going to ask a question. Did it work? Oh, you need to put your blue tab up.
Oh.
It worked? All right. Looks like everybody's worked. Blue tab's down. So we now have the residuals. What do we need to do with the residuals? We need to run a Shapiro-Wilk test. What's the command for that? Shapiro.test. Run that on the residuals. And you will find data are not normal. Are they super not normal? They're not super not normal. They're just a little not normal, right? Do we care? How can we figure out if we care? Make a histogram of it. Look at those data. Do those data look normal or not? What's that? They look a little peaky, and they also look like there's maybe a little more out in the right-hand tail than in the left-hand tail. How can we tell if there's more out in the right-hand tail versus the left-hand tail? Well, we can run a QQ plot. And what we see is that there are more observations out here in the right-hand tail than there are in the left-hand tail than we would expect. So it's a little too peaky, and it's a little skewed to the right, but it's not terribly skewed to the right. This is a normality test. What is the degrees of freedom for this normality test? Yeah.
I have a question.
Yeah.
I don't know what happened, but I told you this one.
Oh, I don't know. Start a new session and just run your code up to this point because your code should all be fine. Sometimes that happens to me also, and it's just a mystery to me why it does that. Might be that it's running out of processing memory on your computer and it aborted, so restarting will clear that out. The other thing that you can do is when you get back into it, use the broom to sweep out your environment, and use the broom down here to sweep out all of this stuff down here. That just clears up the memory that R is using. Yes, ma'am.
I think I didn't load a package because it won't do this. Or am I doing?
Okay, so we're just doing, yeah, we're using R's base graphics, so you shouldn't need anything but R installed to do this. So I can't imagine why it wouldn't be running. Histogram. Try hist. Okay. Oh, do you have ggplot run?
Do I just check it in here?
You can, but they're in alphabetical order, so ggplot's going to be up. Oh yeah, I'm not sure why it didn't do that. Anyway, we got it through hist. Go to your plots. Yeah, there's the plot. Orange tab. What do you got?
When I run my histogram, it looks like this.
Oh, that's weird. Not histogram model 1, histogram res 1.
I changed it back. Because I thought maybe.
Oh, that's weird. Try that. I have no idea. That's weird. Oh, that's bizarre. Let me look at model 1. Oh, model 1 is not giving you the correct values. Temp C. Oh. Okay, hold on. Let's go back. See, your ANOVA table and my ANOVA table are different. So let's see what's going on. Let me see. Run the head so I can look at what your data frame looks like. Why is all your attempts C1? All right, go back. Reload your data file. Now look at it. No, don't look at it with structure, look at it with head. So it's still there. So let's see what you've done along the way. I'm going to change this to declutter a little bit. So, so this should just run that. 1255. Okay, so now you're going to change types to factors. Oh, I know what happened. When you changed it to factor, it was trying to make all those numbers into factors, and so it just assigned them the value of 1. So go through all of this, but don't do anything to temp C. Yep, just run it, run it, run it, run it. Go down to the next set. Go ahead and head the data frame at this point so I can see it again now that we've done a couple of things. Still has temperature and temp C. Okay, continue. You don't need all that structure because we just looked at it. There you go. Awesome. There it is. Yes. All right, now run the residuals and run the histogram on that, you'll be fine. Yes, ma'am.
My graph keeps showing up over here. How do I make it over here?
Go up to this gear, have it put chunk output in console, and then have it remove the output. And what that does for me is it cleans up this frame where I'm actually doing my editing. It'll put everything here and here. Now rerun that histogram and it'll pop over there. There it is. Yeah. Yeah, Cole, you got a question? Oh, okay. Yeah, so remember that when you get into R Markdown, it's going to default to putting your outputs here. I don't like that because it clutters up the space that I'm trying to work in. So I go up to the gear up there in the bar above the editor, and in here you can tell it to put the chunk output in the console. What that does is what you run in your editor appears, the output appears in the console, but then the graphs appear in the graphing box to the right. And for me, it just keeps my workspace cleaned up and not all cluttered up. So we found a deviation from normality. Why should we not worry about the deviation from normality in this case? Okay, so specifically, what do you mean by that? We have 182 data points. If you have 182 data points, even if this data frame is really similar to normality, you're still going to detect a difference simply because you have a huge amount of statistical power. So you're crushing it with 182 data points. You have the power to observe little tiny deviations from normality. And even with all that power, you're only observing a deviation at the 0.04 level, which is right on the edge of significance. What's the other reason? What do we have as sample sizes for each of our treatments? $30, $40, $52, $60. What can we do? What can we claim to the generator of this data about normality? we have a sample size of 30 or above, what can we say? We can't claim that it's normal, but we can claim that we don't care why. It's statistically not normal. We just ran a test that shows it's not normal. It's a test with a lot of statistical power, but it's still not normal, whatever not normal means. If we have 30 observations or more, though, what can we say? From the very beginning of class. Central limit theorem. We're making inferences about the mean, and the central limit theorem says that if you have large enough sample sizes, the distribution of sample means will be normal regardless of what the shape of the underlying distribution is those sample means are drawn from. So we can basically invoke the central limit theorem and say all of our data treatments are 30 values or above, so we don't really have to worry about this small deviation from normality because our distribution of sample means, which is what we're going to be testing, that distribution of sample means is going to be normal. So you know what we say to the non-normality test? We say it's not really that important to begin with because ANOVA is robust to deviations from normality, and we always have the central limit theorem saving our butt anyway. Yes, ma'am?
I'm having another issue. It's not.
So are you using the same variable names as I am? So let's see.
It's saying I can't find summary SE.
Oh, do you have RMISC as a package run? So remember, summary SE is found in package RMISC. So make sure that you've loaded RMISC. Did that do it? Okay, cool, awesome. All right. So for this data set, I'm not going to worry about normality. Normality is not a very problematic deviation to begin with. ANOVA is relatively robust to deviations from normality. What's trickier here is Levine's test. So let's run Levine's test. Levine test on model 1, and what you should see is a really bad p-value. This is the p-value from testing Levine's test. These variances are not similar. If you look in your textbook on page 193, what you will see your textbook author saying is a very important assumption is that the variance of the error term should be appropriately equal in each group. And they say the same thing that I say, which is the assumption of homogeneity of variances is much more important than the assumption of normality because they're right, because they know what the heck that they're doing. So this is a pretty significant difference in the variance. But they go on to say on that same page that testing for homogeneity of variances is problematic. Why is it problematic? Well, it's problematic because if the sample size is really large, these tests could reject the null hypothesis of equal variances when the F-test would still be reliable. What is it that makes homogeneity of variances such a problem for running an ANOVA? I've drawn this diagram, I don't know, about 3 dozen times now. Do you guys remember this figure? Homogeneity of variances is a problem when you have one sample that is really variable, another sample that is not variable, such that the mean of one sample falls within the 95% confidence interval of another sample, but the mean of the second sample, this sample, does not fall within the confidence interval of that sample. And so you're left with this ambiguous decision to make. Are these things different or are they not? Well, it depends on which way you're looking at it. If you're looking at it from the standpoint of this variability and this mean, they're not different. If you look at it from the standpoint of this variability and this mean, they are different. So homogeneity of variance violations cause problems because it reduces our ability to make unambiguous decisions. And we want to make unambiguous decisions, not ambiguous decisions. So if the sample size is large, these tests could reject the null hypothesis of equal variances even when the F test would still be reliable. So what you have to ask yourself when you see a significant homogeneity of variances question is the homogeneity of variance question going to be such that it's causing this problem? How can we look and see if that's going to be a problem with this particular data set? What did I just draw up there? I drew up some distributions, right? How can we make distributions of our data? We've already done it once in this class. We're going to make a histogram. But in this case, we can make a histogram of each of those treatments. So let's get summary data from this data file and save it as CI plot. We've already done that once already without saving it, but this saves it as a data frame. Blue tabs up when you've got this done successfully. You can actually just copy the code from up above and paste it down here and then give it a name. While we're waiting for everybody else to catch up, if you finished, compare the differences among the means that are in the TIMP-C column with the confidence intervals and see how those look to you. Okay, good. Blue tab's up when you've got it. You don't have it. What's up?
I just.
Oh, you're still. Okay. Okay, you've got it. All right. Now call it up. Type its name. You should get in the habit of command return. It's much faster than going up and clicking the run thing every time. All right. So what you should see is that the confidence intervals do seem to change. 1.12, but that corresponds to the smallest sample size we have. 0.77 is the next smallest sample size. 0.34 and 0.548 are for the largest two sample sizes that we have. So it looks like one of the main things that's happening here is that the variation is tied to sample size, which we already know that that's the case because you divide variance by the degrees of freedom, and the degrees of freedom is just 1 minus the sample size. But more particularly, when you look at Galveston in the winter, the average temperature is 25. That's almost 26. That's very different from 29 or 30, and that's also very different from 15. So when you look at this temperature and this confidence interval, there's no way that these means are going to be found within its confidence interval, and there's no way that this mean is going to be found within its confidence interval. So we don't really have this problem. Another way of doing this would be to actually make a histogram of this where you have all four things plotted. So come down here, make yourself a common formatting block. If you have this block from some other script, go grab that block from that script and plunk it in here. If not, you're going to have to just type all this stuff out. The reason I want a relatively clean graph is because we're going to be looking at the details of the graph in quite a bit of detail. So first, form your common formatting block and call it something that's easy to remember and easy to type. Remember, this is just telling you where to put the plot title, what to do with fonts, and getting rid of the grids on the background and all that stuff. You're basically cleaning up your plot before you generate your plot. And I'm going to show you some neat tricks in terms of plotting things. Take your blue tabs down now and put your blue tabs back up when you've completed this typing exercise. I hate typing exercises, which is why I put in common theme blocks. Cole, this is going to be prone to typos, so just pay attention to that. Oh, you just copied it from another script. Okay. Then put your blue tab up. Show me that you're done. Yeah, if you still have a script open in R from a prior day's work, just go to that script, copy it, and paste it in here. It should be the same. Because that's exactly what I did. I copied it from another script, pasted it in here. Yeah, anytime you can copy and paste something that's working and then just change the variables or the data frame or something like that, you're way better off doing that than building stuff from scratch. Because you're taking something that you know works and then just changing what's being plotted, for example. For those of you who are finished with the plotting block or the formatting block, this is the code that you will need to generate the histogram that I want you to generate. So you will also need this, and here's the reference to the formatting block. It's a race against time to see if we can finish this before class is over. Trying to generate the histogram. Okay, good. Run that to make sure that it works when you're done. Rachel, you figured out tab complete. Awesome. Tab complete oftentimes will save yourself typing errors. So as you're typing a command in, R automatically puts up a set of suggestions, and you can just hit tab and it will complete that command for you. It took me a long time to get in the habit of using tab complete, but now I use it quite a lot. Oh, you have a histogram. Awesome. Yeah, if you're done with the theme block, go ahead and put in the histogram code and generate the histogram. And what's that?
symbol.
Panel.grid.measure element.
Obviously, there is one.
Comma continues us to the next line. Oh, but it still didn't. Oh, now you have to call it up.
Yep.
Oh, you need to do the histogram.
Yeah,
Okay, yeah. Okay. That is what it's supposed to look like. So you have Oklahoma City winter, you have Galveston winter, you have Oklahoma City summer and Galveston summer, and they're overlapping one another, which is kind of what you want. They're semi-transparent, so you can kind of see other colors in front of and behind, but you can even make the transparency less by reducing that to like 0.2. And so you can see kind of both colors where they overlap. But yeah, that's what it should look like. Yeah. Element text.
Oh.
Okay. It's saying that data is not found. So I go up here.
Oh, it's because I don't have it as
What's your data frame name?
X.
X. That's X, not that. No, not that. X.
There you go.
Now run it. See if that works. But you still didn't get a... Oh, you have to call it up now. So now call it up. New line. Hgram. There you go. Panel grid, not grind. There it is. All right, everybody have a histogram? No. All right, everybody's got a histogram? Cool. So you run the histogram, and what you should see is that when you look at this histogram, you find that Oklahoma City winter is way over here and doesn't really overlap with Galveston winter. Galveston winter is way over here. It overlaps some with the summer data, but not a lot. And the summer data all overlap a lot, indicating that the two sites in summer are probably not different, but both of these sites in summer are different from both of the winter sites, and the two winter populations are different from one another. Well, we can also then go and add to this. Remember, if you've saved a plot as a name, you can add to this. So let's go back to the CI plot that we conducted. So remember that CI plot looks like this. It just has the mean and the confidence interval. Well, we can calculate the upper limit and we can calculate the lower limit and add those to the frame, the data frame. So do that really quickly down through line 171. Once you check to see that your CI plot has the upper limit and lower limit in it, I want you to then add to your histogram this code here, which will add vertical lines. And the vertical lines will put vertical lines at the average value, the upper limit, and the lower limit for each of these treatments. When you run it, it should look like this. So when you have this histogram with those lines on it, put up your blue tab. Rachel, are you killing it? You're killing it. All right, awesome. Drag your window so that you can see that thing wider. I'm leaving my window narrow so people can still see the code. I'm going to keep you here just a little bit late because I want to make this point. Yeah.
It's working, but should we reassign just
Nope.
this in here?
Nope.
When you retype? Okay.
You're just doing hgram and then you're adding to that. You could reassign it, but you would have to. It's not going to save it like that. So you can just go out here and on that line just do hgram and then use the assignment operator. And then it will save it as that final graph. Yep. So you run that line, run that line. Yeah, there you go. Yep, exactly. All right, looks like most of you have gotten there.
Oh, I'm sorry.
Yeah, what's the problem?
It's not running my selected lines either way.
You're not in a code block. How are you getting that thing to run without code block? Yeah, all that stuff. Yeah, so this is in a code block. Oh no, that's still in the same code block. Oh, that's weird. Yeah, I'm not sure. Stay after for a few minutes. I want to make this point because I want people to be able to leave. But this is an important point. Your job as a data analyst for somebody that is relying on you is for you to not only give them the correct analysis, but also help them understand why you made decisions the way you made them. So what we've done is for the Oklahoma City winter, we've plotted the mean and the 95% confidence interval. We've plotted the mean and the 95% confidence interval, and then for each of these, we've plotted the means and the 95% confidence intervals. This is the main variance that is causing the homogeneity of variances test to be significant. But as you can see, these means do not fall within these confidence intervals. This mean doesn't fall within those confidence intervals. So this problem that is usually going to be a problem incurred by a lack of homogeneity of variances, that doesn't affect your interpretation of this data set at all. And it's because the variances are very small compared to the differences among the means. And so what I would tell a person who is looking at this data is I would say, don't worry so much about the homogeneity of variances because it's not causing the problems that homogeneity of variances normally causes. You can demonstrate this to the person who gave you this data by graphing the actual data and then pointing out where the means and the confidence intervals are. And you can show this is easily distinguishable from that. This is easily distinguishable from that. This is easily distinguishable from that. And these are not distinguishable from one another, but these are the two with the smallest variances and the variances closest to one another in reality. That's because these really are not different from one another. This one really is different from both of these, and this one really is different from this one, and this one is different from all of these. So this problem doesn't exist for this data set because you have the first of these things happening. You have huge data sizes, so you have huge samples for each of these treatments, which makes finding variances different very easy. So you can have a significant rejection of the assumption of homogeneous variances that still is not going to cause a problem for the overall ANOVA. So I would advise the person to just leave the data in their original form, and I would explain this to them using a graph, something like this. And that's part of your job, is to help your person that you're working for to understand what the decision was that you made and to explain to them why you made that decision the way you made it. Thanks for hanging out 5 minutes late. My apologies, but hopefully this will help you as you proceed over the weekend to work on this project. Orange tabs, things that went well, that didn't go well. Blue tabs, things that did go well. And I will see you on Monday. Rachel, am I still meeting with you at 1:45? 1:35?